So now let me get back to the problem of factorization. And what I said at the end of last lecture, that one can factorize a number through solving a problem which is called period finding. Okay. So what is this procedure? So first let me define a function which is a raised to x mod n. Well, I have to give all the notation for various values of x. So a raised to 0 is 1, and keep on multiplying by a at every iteration, and this forms a what is known as a cyclic group. Okay, it's sooner or later all the values will get exhausted because of this modulus n. There cannot be arbitrary large values, and when it starts repeating, we call it a period. So it's defined by coming back to the starting point. Okay? And r is the smallest such integer. So n is a number to be factored, and we will need to specify how many digits does n have. So in our standard place value system, you want to cover all the numbers from 1 to n, you need log n number of digits. Okay. You want to make it more precise, then you can define little bit carefully. We will be dealing with base 2 calculation only. So you start with the smallest numbers, 0 and 1, no problem, it requires only 1 bit. But when you go to a number 1, then 2 will be specified at 1 and 0, it requires 2 bits. Then next step is you go to 4 will require 3 bits, 1, 0, 0. And so you can explicitly write this as the largest integer in defining log n plus 1. So 0 and 1 no problem, but when it becomes 2, then log 2 of 2 is 1 and you need 1 extra bit. That's how it goes. And a has to be chosen. So it is chosen to be co-prime to n. What does co-prime mean? Co-prime means that there is no common factor between a and n. If there is a common factor, our life is simpler because I know a specifically, I know its factors, and there is a common factor between a and n. I have already done some job in taking out a factor of n. You have to figure out how to judge this particular statement, but right now this is a definition. So now ask what can be done with this function. So first of all, the function is periodic, but what is the range of this r it can take? Well, it has to go through n numbers, 1, 2, up to n, before it can exhaust all the possibilities. If you are unlucky, if you are lucky, then you might have to have some things which are skipped and you get to this point faster. But in the worst case, which happens when the group actually is a what you call group with a prime number, and the period can be as large as the number itself. So R can be as large as actually n minus 1, because you are starting with 0. And which makes the problem of finding the value r this is classical. If you are just going to keep on doing addition and multiplication, r can be very large, and then the algorithm is order n to find r. And so to factor n, as I will come to. But this is worse than the simple algorithm we learned in school, which is just divide by all prime number up to root n and see any one of them survives. And this is the name of Erato spelling. Erato So even the symbol algorithm, this is the worst problem, because it's order n and not root n. So you are actually starting with something which is not a good algorithm, but when you convert to a quantum case, it becomes a very good algorithm. Okay. So now, what is the logic? It's quite simple, that when R is even. And of course, there are several things one can easily check. N is odd, because if n is even, in the binary representation, the last bit will be 0. I don't have to do any calculation. 2 is a factor. I do not have to do anything at least to make something non-trivial, n has to be odd. So let us take that R is even. There is no guarantee R can turn out to be odd also, whatever it is, but I am making an assumption that if R is even, then A raised to R equal to 1 mod n can be trivially factorized in this particular fashion, because a square minus 1 is a minus 1 times a plus 1. And note there is a 0 on the right hand side. What does it mean? That the product of these two will produce some multiple of n. Okay. Not n, but it could be some multiple, so there is a chance that something is good inside these two particular factors. Now consider our definitions. This stuff first factor is not 0. Why? Because r is the smallest such integer. If this was true, then the smallest integer will be r by 2, ruled out by assumption. So this is not 0. Can this be 0? Maybe up to modulo n. So a raised to r by 2 plus 1 if I can rule out that this number is not 0 either, this is not 0 as well, and then I can say that, well, both of these things are non-zero, they multiply something, and the result will then give me some multiple of n, so there has to be a common factor. If it is one of them turns out to be 0, then the modulo n doesn't do much, and it doesn't do any good job. So provided r is even and provided this factor is not 0, there a raised to r by 2 minus 1 and n have they have a common factor. Yeah.
Why do we rule out the case?
Hmm?
Why do we rule out the case of a raised to r by 2 plus 1?
You have to check. We calculated r by some method or the other, check that this thing is not 0. Because if one of the factor is equal to 0, then this modulo n doesn't mean anything. Because the product of 2 is 0, the other factor could be anything. 0 multiplied by anything is always equal to 0. So I don't want these factors to be 0. I want them to be non-zero.
So a is positive, r is positive, how can that a power r by 2 plus 1 can be?
We'll see. So now the best thing is to illustrate by simple examples. Yes.
Triple sign, then a to the r by 2 plus 1 will be modulo can be equal to 0.
See, what means that this has led to a situation, this does not, it is non-zero by definition. Okay. If this is not 0, that means it is not a multiple of n. Okay, so if n has some factor, that factor has to come from here. It cannot come from there because it's not a multiple of n. So this is a formal argument. The best thing is to give very simple example and see how this thing works. So that is what I can now illustrate. Okay, I will take various cases where the factors behave in peculiar manner. So first thing is, let me take n equal to 15 and a equal to 2. Okay. So that means a raised to x. What is the sequence? I will start with 1, 2, 4, 8, and I hit 1. What is the period? So r equal to 4. 2 raised to 4 is 16. So now apply this formula. A raised to r by 2 minus 1 and a raised to r by 2 plus 1. Both give factors of 15. This is the simplest example, everything works. Okay, r is even, neither of these things are 0, they are just directly giving you factors. So one more example, little bit different case. Remember, this 2 is not a factor of 15 and 2 is also not a factor of 9, etc. They are co-prime. What will happen now? So a raised to x, 1, 2, 4, 8, 16, and it is 64, which is a multiple of 9, that is 63 plus 1. The numbers can keep on going. There is no limit of that it has to be less than n. A raised to x can be much larger than n before you see this thing repeating. So now what is r? It is from log of 64. So 2 raised to 6 is equal to 64. Okay. So now what are the factors? A raised to r by 2 minus 1. This is a cube minus 1, which is well, 7. And a raised to r by 2 plus 1 is equal to 9, that is equal to 0. So the number was even for the periodicity, but these two do not provide any information. Why? Because this factor becomes 0. And then there is no constraint on this thing having any value related to n. One more example which I had thought of, which wanted something which is r equal to odd. So let me take n equal to 26 and a is equal to 3. So then a raised to x goes as 1, 3, 9, and 27 is equal to 1 mod 26. So R is equal to 3. So that I kind of omitted by assumption that I wanted R equal to E1, so I can do this factorization. But any other power of a raised to R minus 1 can also be factorized. And that is, in this particular case, a minus 1 times a square plus a plus 1 is equal to a cube minus 1. A raised to R minus 1 always has a factor which is a minus 1, whether it is even or odd. So I omitted it here, but you can be lucky that you know what the factorization of this thing is. And then again, the same logic applies that, yeah, it can have something which is a factor of this capital N which you are trying to evaluate. And in this particular case, you evaluate a minus 1, that is equal to 2. And this is 3 square plus 3 plus 1, that is equal to 13. So you got lucky, you actually get factors of this stuff, even though you did not look for that possibility automatically, but that is sufficient. Well, if you turn out to be R equal to odd number, you can try this. It may not work, then you go back to choose another A. Okay. So the criterion is that if these things don't work, choose a different A. And you have to restart. And in that sense, the algorithm is a probabilistic. Sometimes it works, sometimes it doesn't work, and you actually have to estimate what is the probability of success. If it is not large, then this whole machinery is not going to give you anything practical. And now comes a question of proving all the bounds for all the various assumptions which have been made. And that is a subject of number theory. How do you find the probabilities of various assumptions which have been made here? So you have to start all the way from simple arithmetic. What is a prime number? Prime number is a number which the factors are only 1 and itself, no other factors. Then the next question is how do you find prime numbers? But before even going that far, how many prime numbers are there? And it is easy to argue that prime numbers are infinite, never stops. If you really want to find out how many prime numbers are there below a certain number, then it is a hard work. But even that mathematicians have worked out. So there is a well-known results of various category. I can sort of quote it because more or less the things are obvious. So the first thing is any number n can be written as a product of prime factors. It's kind of seems obvious, but this decomposition is unique. There's only one way to write a number as a product of prime factors. And this is something so basic that it's sometimes referred to as a fundamental theorem of arithmetic.
AR by 2 minus 1 and then
Yeah,
last sentence.
this,
So should it be AR by 2 plus 1 and then
it is plus 1 because this one can never be 0. But this can be 0.
you have written
This is minus 1 only.
then here 7 and 9
Because this thing becomes 0, I cannot produce this. This is true only when this one is non-zero. You have to rule out this and then only you can conclude this. If this is 0, you cannot say anything about the first factor because identity becomes trivial. So this is kind of elementary fact. We have used it all the time in starting from whatever primary school kind of stuff, that you can decompose any number as a product of its prime factors, and the decomposition is unique. Some factor can be repeated multiple times, so I put a power here for every prime number, but whatever it is a unique decomposition. The other thing is proof that all prime numbers are what you call never bounded. This is thousands of years old kind of argument, but it can be very easily seen also that if the set of pi are all somehow make a list, take some number and list all the prime numbers which are smaller than it. Then product of all of them plus 1 is a prime number. Because you tried dividing with all of these things, this will give 0 and the remainder is 1. And that means prime numbers never stop. You can't say that all the prime numbers are exhausted below a certain limit because there is one more.
This capital N is prime number or not?
What?
This capital N, less than capital N. What is this capital N?
Doesn't matter. So it never stops. And you can ask how many those things are. And that was a result which took a while to get proved, but the answer is simple enough that number of primes less than n grows as n n divided by logarithm of n. This is the natural logarithm to the base e as n goes to infinity. So not only it never stops, there are lots of them because this log is sufficiently small compared to n. Yeah, so the proof can be given for this statement. Also, it involves application of Riemann hypothesis in some sense, but it's a little technical. I will not go into the detail, but this is a rigorously established statement as well. So yes, we now have some elementary statements about prime numbers. There are lots of them. You can use them to decompose any numbers, and now I can answer all these various questions one by one. So the first thing which I stated, which was a little bit more, that A is chosen to be co-prime to n. What does it mean? That A and n do not have any common factor, and that is rephrased at the so-called GCD, greatest common divisor of the two numbers is equal to 1. Okay, now this GCD again we calculated in school by actually doing factorization, that you factorize one number, factorize two numbers and cross-check it is appearing in both the lists, it is part of the GCD. But that presupposes that I know how to factor. How do you calculate GCD without knowing the factors? And that is a algorithm which goes back to Euclid. Somehow I never learned this thing in school, though even once you look at it, it is very simple. So what does it say? That if A, B are co-prime, means GCD of A and B is equal to 1. But how do you find GCD? And the algorithm is fairly simple, which says that I have two numbers and I assume them to be some order let me check A is larger than B. What the algorithm does is just uses the same procedure over and over again, and that divide the larger number by the smaller number, and the answer, well, the GCD remains unchanged. This you can write it as a, well, various notations are there. It's a remainder of A divided by B. So all you have to do is perform a division. How many steps does division requires? Well, it's same as multiplication by some one digit, whatever it is, that you again do it in school. So the effort is the same as that for the multiplication. So now, what do you do when you divide the number? Well, you look at the first big number and there is a small number. So you look at the first digits of A, as many as whatever they are in B, find the multiple, subtract it, then bring down the next digit, repeat the process, bring down another digit, and so on and so forth. The point is that division of that bringing down one digit at a time appears fast. Why? Because how many times you have to bring down the digits one by one? As many digits are there. It cannot be more than that. And the number of digits in a number of some value is log. So repeated subtraction which you use in division cannot be large, even though the number may be large. How many steps are required? So the division requires it's essentially subtraction. So order that may give this quantity as it is no different than the multiplication. Because you do a one subtraction, then you bring down one more digit, another subtraction, etc., and that is all number of subtractions times number of digits. Subtraction takes order and effort, and so whatever it is with order and square. But you have to use this thing repeatedly. Okay. And that means when I use it once, after this number became smaller than that, and so I have to divide B divided by whatever this stuff is there and keep on going. And how many steps does it require? Well, one can easily prove, again, because the property of the division that every time one digit becomes less, whatever it is. So number of iterations are two times the number, or since I was writing and I can put that thing as well. One can say that this is much more specific, that which number of the two of the which in this particular case I assume to be B. And well, what will happen? The numbers will keep on shrinking, and you will reach two possibilities. Okay, it's if the smaller number becomes 0, that means you divided this division perfectly, there is nothing left. The other number is the GCD, and if number becomes 1, then the two numbers are co-prime. So this solves the problem, but it actually does a lot more than what is written over here. And again, you can illustrate it by examples. So let me take some trivial stuff. Say two numbers. There is a GCD, which we know it is in this case is 5. What happens? So I divide this by this, or 25 by 10. So then it is 5 and 10. Then I divide, the number will hit 0, and then whatever remains, the other thing is GCD. This, let me take something else, say 25 and some other number, say 6. Well, 6 becomes very quick. Let me make life a little more complicated. So let me make it 7. So what will happen in this particular case? 7 times 3 is 21, so you divide, it will become 4 and 7. Then you divide again, so it becomes 4 and 3, and then you divide again, it became 1 and 3, the smaller number became 1, so these numbers are co-prime. Of course, if I do one more step and divide by 1, you will hit 0, but you don't have to go that far. Okay. So this algorithm basically only works with these remainders, and the number of steps, as I said, is log n of the smaller numbers and the total effort. So is n cube, n square for division times how many iterations are there. So it is nowhere near this capital N, it is much smaller. So that is the first step, that this have to be co-prime. Now, there is something else which is buried inside here, because I did the division, but I only kept the remainder. I can keep the integer part also if I want to. And then the statement will go that a, b is equal to some constant times b plus the remainder, comma b, and that whatever constant times b can further be re-expressed by dividing by whatever is there in the remainder, etc. So, if the integer is kept in this particular process, then this statement can be rewritten as a times x plus b times y is equal to c. Where what are x and y? Where the x and y will come from the integer parts. This is the equivalent statement of what the greatest common divisor means, that there will be some multiple of one number and some multiple of the other number, such that the linear combination is C. There is no mod.
C is greater than A and B.
Well, x and y can be negative. For integer, they don't have to be positive. Because I'm performing a division which involves a subtraction.
So how is the effort n cube? How is the effort n cube?
Because division required order n square, and the number of steps involving successive divisions is equal to number of digits, so you multiply this n square by number of digits, which is order n cube. And again, the best way to do this thing is, again, take the same example. We'll see. Let's see us work with this. So we went through this. What will happen? I will keep the integer part. So 25 is equal to 2 times 10 plus the remainder. Okay, this was the first division. I kept the integer part which was discarded over here. Now, what was the next step? I was going to divide 10 by 5. Okay, So I rewrite this 10 is equal to 2 times 5 plus this 5 is still hanging around, no problem with that. And then you can simplify. This is one integer, this is another. So it is 4 times 5 plus 5. The point is I can reduce everything in terms of the second number. And it lands up with a statement like this. Now I can look backwards. 5 turned out to be the GCD. Okay, so I can rewrite this thing. So go backwards, and then I can express this relation in terms of some original numbers and some x and y. So this is equivalent to this. Not only that, the algorithm tells you how to construct it whenever needed. And yes, signs will appear. Okay, so x and y can be positive, negative, whatever it is. That can happen. There is one more thing, that this is where it had a factor, and I can use the same strategy that for co-prime case, I have A times x plus b times y is equal to 1. And I can define A times I is equal to 1 mod b, and then x is the inverse, reciprocal. This modulo b is a peculiar part of the arithmetic. Inverse don't have to be fractions. They are another bunch of integers.
That equation implies this a into x plus b into y equal to 1.
Huh?
Ax plus by equal to 1 implies this ax equal to 1 bar b.
It implies this. Of course, because this thing will just drop out when you take a modulo b operation. And this is something which one has to get used to in number theory, that you can define inverse. The inverse number is also an integer, and that results from the fact that this is some modular arithmetic. But this is a very useful concept, that if the numbers are co-prime, you can define inverse.
Can't be like one is like something a to the r mod b, and then if I take like x a inverse, that becomes a to the r minus 1.
You don't need higher powers. This is enough at the linear level. So, yeah,
Here, the number of iterations are at most 2 times of log 2 in the fifth.
yeah,
The GCD calculation.
yeah.
Then it should be n square times log 2 in, right? So n square times n.
Small.
If you want to, instead of write 2n cube, doesn't matter, because this order notation does not worry about constant. But yes, if you want to count these two, and this is n square, multiply, it will become 2n cube. Order notation, you don't worry about the multiplicative constant in front. Number of digits is here. So this Euclid's algorithm is actually a very powerful and simple procedure. It can be used to do all kind of tricks, and well, you can work out various consequences without too much trouble. So I got rid of what is the meaning of prime numbers, then this co-prime checking, which is n minus some power with log n cube effort. Then I have to go to the next step, and that is actually what is the success probability of finding A which is co-prime to n. Okay. It may be that well, as I said, if it is not co-prime, your life is easy, you already found a common factor. But you can ask how far this can be chosen. So that is another exercise, which is how often A and N are co-prime. These are means standard results in number theory, and not too complicated, but one doesn't learn it in schools in any way. So you have to spend some time understanding the logic for it, and once you get hang of it, it's not complicated. So take two numbers. How often they are co-prime? Co-prime means there is no common factors. So I can ask the question that if I take one number and take all its multiples, how many are going to be multiple of that number, and how many are not multiples of that number. So the probability of choosing what you call a random number, or yeah. It's rather trivial. Every PS step, the multiple will keep on repeating it. If I just take a random number, the probability that it is a multiple is 1 over p. It's a uniform distribution. For example, if I take p equal to 2 and a random number, half the time it will be 1, half the time it will be odd. Nothing more complicated than that. So now instead of choosing one number, I choose 2 because I want to compare this. And they are kind of chosen randomly, arbitrarily over this because I want to calculate the probability. So that can be rewritten as this co-prime probability is a product of 2 factors, nothing more complicated than that. Take all the primes and ask whether it's a factor of the first one or the factor of second one. And both of them have to fail. But there is no common factor. So each one has the failure rate of 1 over p. I take the joint probability, it is 1 by p square, subtracted of 1.
This p is a prime number. This p
Is a prime number. And now this is a product of all prime numbers. So can I evaluate this? The answer is yes. So let me give this some value. It is well, just let me call it some other variable q. And yeah,
These prime numbers, they're bounded, right? They can't just be greater than the.
doesn't matter, even if you take greater than that, the co-prime statement will remain true. It's not going to be a factor of either of them. And it's easier to evaluate the whole infinite series. So this looks kind of funny, but what is easier to evaluate is 1 over q. So that is product over p and so this can be rewritten as 1. I will do a simple Taylor series expansion for these factors, and reciprocal of 1 minus x is 1 plus x square plus x cube, just geometric series. Okay, so 1 over p1 square. Keep on going. And now we can do a big rearrangement in our mind. What happens when you multiply these particular factors? So what you will get is some factor from here, some factor from here, some factor from here, etc., etc. And they are all in the denominator. And it is a product of one prime up to some power, another prime up to some power, etc., etc. And then look at this. It rearranges all these things in the denominator. On top of that, it's a unique decomposition. So this is a remarkable sum which can be performed. Uh, and this is, well, starts with 1. It's a well-known series. You may have evaluated it in some form or the other. And it has a value which is quoted in various ways. One of the ways is called a zeta function. If I take this whole thing to be infinite. If it is, you want to truncate it at some stage, well, the number will be smaller than this. And so, this co-prime probability is at least this. If you truncate it, then this number will become smaller and this number will become larger.
That capital N, where unit decomposition is written, that capital N and this small n equal to p1 to power alpha 1, p2 to power alpha 2. These two are same.
Yeah, because it's a unique decomposition. You imagine multiplying all these factors. What you will get in the denominator, p1 raised to some power, p2 raised to some power, p3 raised to some power, and every combination will appear only once. And whatever that once appears, it has a unique decomposition, which is exactly some powers of prime. So the probability of two randomly chosen numbers to be co-prime is something like 60%. At least 60%. So we answered, well, one more question, this. Now the last question is the probability of for n which is odd. These are the two situations I want to rule out, because this thing worked only when R was even and this factor was not 0. So I want to rule out that either that thing is odd, the period is odd, or that factor is equal to 0, the opposite of what I require. Is less. This is the answer. Where the m is the same m which appears over here. M is a number of prime factors. And that means probability will be less than half if there are two factors. Probability of failure is less than half. There are two factors, but if there is only one factor, it can be, and n cannot be, n may not be prime in the case n is a power of a prime number. Then there can be multiple factors. Then this proof of this statement fails. So what are called prime powers if you want to use this algorithm, then you have to make sure that the number is not a power of a prime number. Then only the success probability is larger than half. Otherwise, you can be running into a problem. Fortunately, there is a test for checking whether the number is a power of a prime number. That's another exercise, but you have to rule it out at the beginning before you start using this periodicity algorithm. How can you prove this? Well, the proof is a little more complicated, but there is an important ingredient inside the proof which is again well known, and it is a powerful result known as the Chinese remainder theorem. Again, it's quite old, but it basically provides you a way of combining multiple prime factors and finding out how that combination will behave. And we need to do that to produce this particular result. So what is the statement of this Chinese remainder theorem? It's actually let mi be a set of prime numbers, some set, and then solve x these are simultaneous equations. It's one variable number which is x. When you divide with mi, it leaves remainder ai for different values of I. So the job is to find such an x. You are given a prime numbers and you are given all the remainders. Okay. And there is an answer. And the answer, the easiest way to describe is actually by explicit construction. Okay, just like Euclid's algorithm tell you that you do this, you will get an answer. You may have something else beyond that, and the answer, because of the modular arithmetic, doesn't have to be unique. Things repeat after certain numbers or periodicities. But find one answer that is kind of good enough. So what is the proof? Well, so we'll define let some capital M is equal to product of all of these prime numbers. And another number mi, which is from the whole product, you leave out the one which is the equation you are looking at. Okay. So now the statement is that very easy to state that mi and mi are co-prime. So they are all different numbers. You take out one, whatever remains are all different ones. What does this imply? That there is a multiplicative inverse. The modulo arithmetic is respect to mi. There is some number, it is co-prime to it, I find an inverse, some other integer. Then x, what does this look like? This answer.
This character is multiplicative inverse.
Yeah, ni is a multiplicative inverse of ni. And now you can ask why it will produce this particular result. There is a multiple sum. Okay. So now I ask what is the result for each index I one by one. Okay. So just take the first term. Okay. If I take mod with respect to any of the other numbers, not the first one, this summation will contribute 0 because all the other numbers are contained in capital Mi. They are here. So the only term which contributes is the one corresponding to I. When you take this mod, all the others disappear. And now what happens when I take mod Mi? Well, I define this to be an inverse. So that is 1. And then it is AI, that is a term which survives. So if I now consider some others, it's x, inner mod mj operation. Then if j is not equal to I, terms do not contribute. Because mi mod small mj is 0 or I not equal to j, and j equal to I term has mi ni equal to 1 mod mi. And yeah, this is just an explicit construction. You can solve all these multiple equations with different prime numbers and some remainders to find an answer. One more statement I can make: any other solution has x prime is equal to x plus some multiple of this big number. Because this big number has all the primes on it, you take a modulus operator and it doesn't contribute. So this is a Chinese remainder theorem. Again, the arguments are, well, something to be digested, but they are not too complicated. And this is a important ingredient in the proof of this particular statement. I am not going to give a proof of this because it kind of gets little complicated, but if you want to know reference where the proof is given, and also proof of all these statements are also there. It is in the appendix of Nielsen and Chuang book, one of the last appendices. It's basically a short appendix, few pages, but all these results are kind of described in there. There's a lot more than whatever I told you as well. There are exercises as well, but all this description is there, and that now brings us to the statement of what has to be done for this factorization. It's a probabilistic algorithm. There is a reasonable chance of success provided you rule out certain cases, and what you need to rule out is this base on which you are taking a power must be co-prime. The number you are trying to factor should not be a power of a prime, and when you run the algorithm, R has to be even, and a times a raised to r by 2 plus 1 should not be equal to 0 mod n. So all those conditions, if it's satisfied, the problem will be solved. This says nothing about the quantum theory at all. Okay, this is just usual formulation of the problem as period finding. The quantum part comes in only when you assume that all these conditions are satisfied, and this is what I have to do. How do I do it? I want to find the period, but how do I find the period? And that exercise of finding the period has a convenient structure in quantum mechanics, because in general, for a periodic function, the Fourier transform will give you the periodicity. The advantage which comes from the quantum theory is making that Fourier transform is easy. In classical theory, yes, Fourier transform will do the job for you, but Fourier transform is complicated in the sense that it requires a lot of work. The quantum Fourier transform will be much easier to implement, and that is where the speed up of the algorithm comes from. All this stuff is just a standard analysis using number theory, and you have to remember that the algorithm is probabilistic. If it doesn't work, repeat it. The only thing is we have calculated various probabilities that the success probability is reasonably large, so the number of repetitions required are not going to go unbounded in any sense. Success probability larger than half, so maybe you require 2-3 trials and then it will be okay. So that is the status. So the next class I will have to now describe how does quantum Fourier transform tackle this particular problem.